Good afternoon, everyone. Happy Friday. I hope that everybody's doing great and you've been having a really good week. We're going to be moving on today and looking at one application of trigonometric differentiation, which is an application of differentiation that you've already covered. It's related rates. And we're going to be doing two examples. These examples can be found on page 10 of your current lesson handout. I want to remind you that when we do related rates questions, there's generally speaking three tiers to the strategy. The first level is for you to identify rates of change that you know or want to know. The second level of your strategy is to look at that list of rates of change so that you can identify variables in the problem that are important. And the goal there is to then develop an equation that relates the variables. The third step, which is the final kind of level here, is once you have that equation that relates the variables, you can differentiate that equation with respect to time, and you will then have a relationship between the rates of change of the variables, and you can use that relationship to solve the problem. Let's take a look at the first example. It says that two sides of a triangle have lengths of 20 and 35. Now, it doesn't say whether it's 20 and 35 centimeters or 20 and 35 inches. It really doesn't matter. So I'm going to sketch a diagram here just showing what that's telling us. We've got a side of a triangle that is 35 long, and we have another side that is 20 long. And you're told that the angle between the sides is changing. Now, in any related rates problem, you are only ever allowed to use in your equations values if they are constant. So I cannot put in a specific angle into my equation here, even though it does tell me that the angle between the sides is pi over 6 radians. I need to wait until after I differentiate to use that piece of information. In other words, everybody, theta, the angle between the sides, is a variable. On the other hand, the numbers 20 and 35 are constants, which means I am allowed to put those numbers in to my equation right out of the gate. They are not changing, they are constants. We're told the angle between the sides, which is theta, is decreasing at a rate of pi over 80 rads per second. That's telling me d theta dt is negative pi over 80, and that is in radians per second. And you should make a note to yourself here that related rates problems only work when you're using radians in your rate of change of the angle. If you ever put in d theta dt in degrees, you will get the wrong answer. It must be in radians. Now, what are we asked to find? We're asked to find the rate at which the length of the third side is changing. So I'm going to draw a third side to this triangle now. And you can think of this third side as being like a piece of elastic. And as that 20 unit length side starts moving in a clockwise direction, because theta is decreasing, that elastic is going to stay stretched, giving us a triangle. And we're asked to find the rate at which the length of that elastic is changing. So we have to introduce a variable for that. Doesn't really matter what we choose to call it. I'm going to choose to call it x. And that means that in our list of rates of change, we are asked to find dx dt. Remember what I've told you before. Your first step is to compile a list in related rates problems of any rates of change that you want to find or that you know. And we've done that. We want to find dx dt, and we know d theta dt. That's the first step. So now that we've compiled that list of rates of change that we know or want to know, our next step is to come up with an equation relating the variables whose rates of change are in that list. And the two variables are theta and x. So we need to come up with an equation relating theta and x based on this diagram, and we're going to use the cosine law. If you were doing this on any type of evaluation, you would be allowed a formula sheet, and on the formula sheet, the cosine law would be given to you, or it would be given to you as part of the question. But the cosine law is used to find the length of a side when you know two sides of a triangle and the angle between them. And the cosine law in this case says x squared equals 20 squared plus 35 squared minus 2 times 20 times 35 cosine of the angle between the sides, which is theta. It would be nice to simplify this a little bit before we go on. X squared equals 1625 minus 1400 cosine of theta. Negative 2 times 20 times 35 is negative 1400. So that's our second step. Our first step is to compile that list of rates of change. Our second step is to develop an equation relating those variables. Your third and final step, which is sometimes where there's an awful lot of work, is to go ahead and differentiate that equation with respect to time so that you can answer the question. The derivative of x squared is 2x dx dt equals the derivative of 1625 is 0 minus the derivative of 1400 cos theta. While the derivative of cos is negative sign, so the derivative of 1400 cos is negative 1400 sine theta, times the derivative of the argument. The argument was theta, so we have to multiply by d theta dt. When we divide both sides by 2x to solve for dx dt, which is what we are after in this question, we're going to have 700 sine theta over x and multiplied by d theta dt. The 1400 divided by the 2 gives 700. We also have to divide by the x. That's why there's an x on the bottom. So now all that remains is we have to put in the numbers for all of these unknowns on the right-hand side. One thing that you want to be cautious of here with related rates problems involving trig is you shouldn't think of theta as something you're trying to find. If you see sine of theta, then that is your goal. You need to determine the sine of theta. Don't worry about what theta is. Theta is actually given to you in this question, but it's not always going to be given, and even if it's not given, you don't necessarily care what the angle is. That will make more sense when we look at example 2. We also need to know the value of x, and we also need to know the value of d theta dt. Well, d theta dt is easy because it's given to you. It's negative pi over 80 rads per second. Sine of theta is not given to you, but in the question it says essentially when theta equals pi over 6 rads. And if theta is pi over 6, then we need to know what sine of pi over 6 is. Sine of pi over 6 is 1/2, and you can determine that by looking at your unit circle. We also need to determine what x is, which is the biggest detour in this question. We need to use the formula that we developed, this formula right here, to find out what the value of x is when theta is pi over 6. X squared is equal to 1625 minus 1400 cosine theta, which means x is going to be the square root of 1625 minus 1400 times cosine of pi over 6. Cosine of pi over 6 is root 3 over 2, which means we now know what x is equal to. X is equal to the square root of 1625 minus 1400 multiplied by the square root of 3 over 2, and the 1400 divided by the 2 cancels to give 700. We know what x is. X is the square root of 1625 minus 700 root 3. So those are the three quantities that need to go into this equation. And what we're going to get for dx dt will be 700 multiplied by sine of theta, which is 1/2, over x, which is the square root of 1625 minus 700 root 3, multiplied by d theta dt, which is negative pi over 80. And now we can simplify that. I'm not going to worry about rationalizing that denominator or even worrying about what that radical can be simplified into. I really don't care. What do we get? dx dt, we have to simplify some numbers here. 700 multiplied by 1/2 divided by 80. I'm pretty sure that is 35 over 8, but we'd better check that. 1/2 of 700 is 350 divided by 80. 35 over 8. We also have a negative and a pi in the numerator, which means dx dt is negative 35 pi over 8 root 1625 minus 700 root 3. And that is the rate of change of the third side, and that would be expressed as units per second. If those two lengths were 20 centimeters and 35 centimeters, then our answer would be in centimeters per second. And by the way, it's per second because the units of the rate of change of the angle was in rads per second. Of course, we can always calculate what this number is equal to as a decimal approximation to get some kind of a handle on it. I would probably calculate what's underneath the square root sign first and go from there. So on the bottom we have the square root of that. That means the bottom is 8 multiplied by the square root of that number. And then on the top we have negative 35 pi divided by what we got on the bottom. Gives us about negative 0.68 units per second. And that's it. Let's take a look at the next question. We have a beacon located 450 meters away from a shore. In an idealized math problem, of course, the shore is a perfectly straight line. We're told that there is a beacon that is 450 meters away. What this means is the beacon emits a beam of light, and as that beacon rotates around this point, as the beacon rotates around that point, it's going to shine a beam of light along the shore. And that beam of light is going to move with a certain speed along the shore that depends on a number of things. One of the things you're told is that the angle is changing because the beacon is rotating. So we're going to introduce an angle into our diagram here. The angle can be expressed as theta if I put theta there. Now, d theta dt is the rate at which that angle is changing in rads per minute. I'm going to use per minute because I see minutes in the problem. The only problem is 4 revolutions is not 4 rads. You need to remember from Math 30-1 that a full revolution is 2 radians. That means that 4 revs is 4 times 2 pi rads, or 8 pi rads, which means d theta dt is 8 pi rads per minute. Now, whether you want to use positive or negative doesn't matter. If you look at the diagram, I don't know whether theta is increasing or decreasing because I don't know which way the beacon is rotating. If it's rotating clockwise, then at this instant in time, theta is getting smaller, which means d theta dt would be negative. But if it's moving clockwise, then as soon as the beacon starts getting below the horizontal in our diagram, theta is going to be increasing. So the whole thought of a positive or negative d theta dt here doesn't really hold water. It has no value. Now, when we're asked how fast is the beam moving along the shore, that means we're asked to find the rate at which this distance is changing. We can call that rate of change dx dt. So here is our list of rates of change that we know or want to find. One of the things that I forgot to put into my diagram, which is crucial to solving this problem, is that this distance is 450 meters. It's crucial because without that 450, you cannot come up with the equation relating theta and x. Tangent of theta will be the opposite side, which is x over 450, and we can simplify that to give x equals 450 tangent theta. That's my second step. First step, all of your rates of change in terms of the ones you know or want to know. Second step, done. What's the equation relating the variables? Third step is to differentiate and solve. So let's go ahead and differentiate this now. dx dt is going to be equal to 450 secant squared theta d theta dt. Now, when you go back and look at the question, there are actually 2 questions. One of the questions says, how fast is the beam moving along the shore, which means what's dx dt at the nearest point? So at the nearest point means that the angle is getting smaller and smaller and smaller, and x is getting smaller and smaller and smaller. And when the beacon is at the nearest point, both x and theta have reduced to 0. The first question then is, what is dx dt when x is 0? That's the first question. If we take a look at the second question, it then says, how fast is the beam sweeping along the shore when x is 200? So there's a second question. We also want to find dx dt when x is 200. I don't know if you remember, but I had said in the previous question that when you do related rates problems, we're not necessarily concerning ourselves with the angle. We're concerning ourselves with the trigonometric ratio. Let's keep that in mind as we work through both of these. For the first problem, our dx dt will be equal to 450 multiplied by the secant squared of the angle, and I'm going to come back to that, times d theta dt, and d theta dt was 8 pi. So what is the secant of theta when x is 0? Well, if you stop and think of the definition of secant, it's reciprocal of cosine. And if we had a triangle which looked like this is the hypotenuse and this is the adjacent. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. This is going to be useful for both of our problems. Secant will be the hypotenuse over the adjacent. But when x is 0, when this distance is 0, the length of the hypotenuse becomes the same as the length of the adjacent. In other words, the secant is going to be 1 because it will be the hypotenuse over the same length. And we have our answer. All we have to do is figure out what 450 times 8 is, and we can write down our answer. I believe it's 3600 pi, and this would be in meters per minute. That 3600 is 450 multiplied by 1 squared multiplied by 8. Now, when we find the answer to the next question, which is find dx dt when x is 200, we're going to go back to this triangle and the idea that secant is hypotenuse over adjacent. For the second question, this number is 200. The adjacent side, of course, is 450. So we can use that to find the hypotenuse. Remember that secant is hypotenuse over adjacent. For our second question then, the answer will be dx dt equals the 450 multiplied by the secant squared of the angle, and we'll get to that in a second, multiplied by 8 pi. Okay, so secant is the hypotenuse over the adjacent. The adjacent's 450. Now, what is the hypotenuse equal to? Well, that's a pretty basic, I want to say grade 7 or 8 question, where you're going to use the Pythagorean Theorem. If I take my 200 squared and add it to 450 squared, that gives me 242,500, which means the hypotenuse is the square root of 242,500, and we are not going to waste any time simplifying that. The reason is, going back to the bottom of the screen, what I have in brackets there is secant. Secant is hypotenuse over adjacent. So the hypotenuse is root 242,500. And the reason why I don't care about simplifying it is I was kind of looking ahead and seeing that since secant is root 242,500 over 450, and I have to square it because we have secant squared in our formula, the square root and the squared will cancel. So I'm not going to waste any time worrying about simplifying that radical. What do I get? I get dx dt equals 450 multiplied by 242,500 over 450 squared times 8 pi. pi. I didn't even waste any time here worrying about squaring the 450 because I have 450 on the top and I have 450 squared on the bottom, which means one of those 450s will cancel, and now I'm getting very close to the point where I can write an answer. I'm going to have 8 multiplied by 242,500 multiplied by pi over 450. And no matter how much I talk about showing all your work and using your brain and all of that, you know, sometimes it's just been a long day and you just want to get to an answer. 8 multiplied by 242,500 divided by 450 gives me 38,800 ninths. Pi, and again, this is going to be in meters per minute. So the answer to the question, what is the rate at which the beam is sweeping along the coastline when the beam is at the point closest, is 3,600 pi meters per minute. What is the rate at which the beam is sweeping along the coastline when the end of the beam is 200 meters away from the closest point? This number. And of course, you can feel free to use your calculator to calculate the numerical value of either of those. I'm not going to do so in this video. I will tell you, though, that you're going to get very big numbers, and they're shockingly big. You're going to get in the neighborhood of thousands of meters per minute. But if you stop and think about it, that makes sense. When you have a light source that's 450 meters away from where it is shining, even a little change in the angle will cause the end of the beam to move quite far. Just like anything else in this course, everybody, right now, the main priority is for you to get better at math so that you're more prepared for next year. Even if you don't take calculus, we haven't talked about this, I haven't mentioned it to you, but I believe one of the most important parts about you following along with this material, even though you're not in the school physically, is it's keeping your brain active. I truly believe that is important. If you let your brain stagnate over the next 4 months and then you get to university, you're going to have to work very, very hard to wake your brain up again. So that's my teacherly advice to you today. Anyway, your assignment relating to related rates, dealing with trigonometry, is 8 through 12. The fact that I've highlighted that tells me that it must be different than what I had in your note package. I think maybe I had 8, 9, 11, and 12. I'm not sure. But you should be able to do any of those 5 problems. Today is Friday, so I wish you a very, very happy and relaxing weekend. If you need any help with anything between now and Monday, feel free to email me. I would be more than happy to get back to you and help you out. In the meantime, enjoy the rest of the day, and we will talk to you soon. Take care.